Hello, this is our class for Wednesday, April 8th. What I'm planning for this class and the next class is review, basically, for the exam that we're going to have over the weekend. So just to remind you, my plan is to not have a time like secure type exam. Basically, it's just going to be like a worksheet with a bunch of questions, not so different from like a review sheet. And you sort of work it over the weekend, and I still haven't decided whether I'm going to put it in D2L or have you email it to me. Right now I'm leaning towards emailing it, but I haven't put it together yet. That's why I haven't decided. So I'll say for sure it'll probably be like on Thursday when I finally like get it posted up and tell you exactly how it's going to work. But I want to spend a couple days reviewing stuff that will be on that. So today I want to sort of go through the list of topics and do some examples. And I'm also going to post a sort of practice exam type worksheet along with the notes and video links on my website. And then tomorrow I'm going to go over the answers to the worksheet. We'll sort of like go through the problems basically. One other thing to mention, normally when there's an exam, we don't have any quizzes that week. That's how we would do it if we were meeting face-to-face. So there is this sort of D2L quiz for the Monday class based on 10.2, but there won't be for the next couple for these review classes. There isn't going to be a D2L question. So basically this week, there's probably just that one online D2L quiz worth 1 point. Okay, so let's talk about the topics then. The first thing is something we talked about when we were still face-to-face, and that is Poisson. So Poisson process and inter-arrival time and the exponential distribution kind of all went together. Here, I'm going to turn off my video just because this will upload quicker to YouTube without the video there. Okay, so these are all kind of together, and they were sort of in the book, but most of it was not in the book. I just sort of worked off of another book. And let me try to sort of summarize how all this worked. So these questions had this number lambda associated with it. Do I have lambda on my standard drops? No, I have to switch to Greek. Okay, so lambda, they had this number lambda, which was basically like how, like the density or the rate at which arrivals were coming. So, you know, our most common example was in terms of time, and like hits or arrivals were happening at random times. And what we knew was sort of like on average how many came per unit time. So this was like the rate or density of arrivals or sort of like successes or hits. So, you know, so it might be like how many people come per hour to a store, or how many like visitors you have per minute at a website, or how many times like some random occurrence happens per year, you know those types of things. Like sometimes it was not in terms of time, like it might be, I think we had an example where there was like steel girders on bridges, how many like imperfections per meter there were on average, stuff like that. So if you have these random things coming in, we had two different types of random numbers we could generate. So the first type of random number we could generate is, in a specific amount of time, how many hits do we think will happen? So first version of a random number is how many hits or arrivals in a specific amount of time. So the random number is how many hits you get. So you know how much time you're looking at, and you don't know how many hits there's going to be. That's going to be random. So this is a Poisson distribution. That's what Poisson was. And the other type of random number we could generate was well, we don't, these hits arrive randomly. We don't know how long it's going to be until the next hit, or if there's 2 hits, how long is it going to be between them? So the time until the next hit, or between 2 hits, that was what we first called inter-arrival time. And then eventually we sort of call it the exponential distribution. Okay. So both of these could sort of be mixed together in the same question. You know, they're based off of the same setup. It just depends on whether you're asking like this time until the next hit, and that's your random number. That's the thing that you don't know, and you want to know the probability of it being a certain amount of time, or you say, okay, there's going to be this much time. How many hits are we going to get, or what is the probability that we get this many hits in a specific amount of time? And so it's either exponential or Poisson. Okay, so let's work through one example of this. I did want to write down my formulas. Okay, so I have that in my notes. So for Poisson, the expected number of hits in a set time, we have a formula for that. So it is kind of messy. So we have e to the power of minus lambda times the amount of time. So I'm going to call that time span. And then there is that lambda times the time span. Oh, no, I'm writing down the formula. Okay, so the expected number of time. I'm writing down the probability distribution. Okay, so the expected number of hits in a set amount of time is just lambda times the time span. Okay, lambda times the time span. Okay, what I was doing here, what I was starting to write down is what is the probability of a specific number of hits. So the probability of X hits in the set time, equals, okay, so let's finish this now. So to the power X, and then the denominator is X factorial. So how many do you expect to happen? Well, you know how many happen per unit time, so you just multiply that by how much time you have. That's the expected value. But if you want to know the probability of a specific number of hits in a time span, then you take that expected value, you put it here in the power with a minus on the exponential, put it down here, you raise that to the power X, and then divide it by X factorial. All right, so for the inter-arrival time, aka exponential, your expected time until the next hit, which would also be the expected time between 2 hits, is just 1 over lambda. Which makes sense. Like if you expect 2 hits per hour, the expected time until the next hit is half an hour. You know, basically, that's how it works. You just divide it. So like 2 hits per hour, 1 over 2 hours until the next hit, and then the cumulative distribution function, the CDF. So this is the probability that the time until the next hit is less than, let's say, capital T, and we might call this capital F of capital T. So that's 1 minus e to the power of minus lambda times t, capital T. So that's our cumulative distribution function, and usually that's the easier one to use to answer probability questions. But we do have a formula for the probability density function, the little f of t, that is lambda e to the power of minus lambda t. T greater or equal to 0. Okay, we didn't use this one very often. I mean, you could find probabilities by doing integrals of this. That was usually the hard way. The easier way was typically to use the cumulative distribution function. So let's do one quick example of this, and then we'll talk about the next section covered in the exam in a separate video. So example, birds visit a bird feeder at a rate of 2.7 per hour. Let's first find the probability of 3 birds in the next 2 hours, and then find the probability the next bird comes in less than 10 minutes. Okay, so this first one, what is the probability that 3 birds come in the next 2 hours? Well, it could be 3 birds in the next 2 hours. It could be 4, 5, 10, 0. We don't know how many birds are going to come in the next 2 hours. We want to find the probability that the number of birds that come in the next 2 hours is 3. So this is a case where the random number is the number of arrivals. 2 hours is the fixed number. So we're in Poisson. So we just have to plug into this Poisson formula the numbers that we are given in the question. So lambda is 2.7. That is our average arrival rate. So that's where the lambda comes from. And the time span is 2 hours. Okay, so 2.7 per hour. In 2 hours, we would expect double that. So 2.7 times 2. And we want to know the probability that that comes out to a 3. That gets plugged in for the x. And I'll spare you me typing this into a calculator. This comes out to 0.1185. So just under 12%. The second half is the exponential one. We're talking about when does the next bird come. That is exponential inter-arrival time. What is the probability that it's less than 10 minutes? That's basically set up for our CDF thing. The probability that the time until the next hit is less than t. Here, the time until the next bird is less than 10 minutes. So I want to basically find capital F of 10 minutes. This 2.7 is in hours, so we have to convert that 10 minutes to hours. 10 minutes is 1/6 of an hour. So we're going to plug 1/6 into this formula for capital F. We have 2.7 for our lambda and 1/6 for our t. And if you stick that into a calculator, what you get is 0.3624. Now, both of these questions can actually be done in Minitab. If you go to like calculations and then probability distributions, it has Poisson and exponential distributions, but we never did them in Minitab. So it takes a little while to sort of figure out where the numbers go in and how to fiddle with it. So it'd be safer to just use these formulas and just stick them into a calculator. That's sort of like the safer way to do it. That's the way we did it in class. Okay, so we'll cut off this video and I'll talk about the other sections in a couple other videos.